Welcome to Study Loop.
So as with any physics problem, we're going to want to start by drawing a picture. This always helps us to get a good intuition about what's going on and visualize things. So we have two cars. One has a mass of 1,200 kilograms, and the other has a mass of 1,800 kilograms. Furthermore, one is moving with a velocity of 12 meters per second, and the other is moving with a velocity of 20 meters per second. And they are separated by a distance of 40 meters. Now, the first part asks us to find the center of mass of these two cars. And since we're not given a specific coordinate system, all we need to do is find the center of mass relative to these two. So we might as well define this one here, the first car, to be the origin. And in that case, we'd be defining its position to be x1 equal to 0 meters, and then the first one being 40 meters ahead of it would of course just be at x2 equal to 40 meters. Then we just use the center of mass formula, which is XCOM, for center of mass, is equal to m1 x1 plus m2 x2, all divided by m1 plus m2. This is called a weighted average. Interestingly, it gets its name from the actually playing the role of a weight to some degree. It's the mass, but from gravity, that's what gives us the weight. So fun fact there, when you plug these in, you have 1,200 kilograms multiplied by 0 meters plus 1,800 kilograms multiplied by 40 meters, all divided by 1,200 kilograms plus 1,800 kilograms. Plugging all those numbers in, we get 24 meters. After canceling the units, or after canceling the kilograms, we're left with just meters. So the next step asks us to find the total momentum of the system. So total momentum is given by the sum of individual momenta, which is just m1 v1 plus m2 v2. And that is simply 1,200 kilograms again. Multiplied by 12 meters per second plus 1,800 kilograms multiplied by 20 meters per second. Multiplying those out and adding them up, we get 50,400 kilogram meters per second. Excuse me, forgot my G there. Next is part C, in which we're asked to find the velocity of the center of mass. We can do that simply by taking the time derivative of the position center of mass expression, which was xcom is equal to m1x1 plus m2 x2 over m1 plus m2. Taking the derivative here, because the velocities are constant, we just get x time derivative of xcom is bcom. Time derivative of m1 is v1. Time derivative of m2, or of x2, is v2. All divided by m1 plus m2. And then from this we have that bcom is equal to, well, one thing I'll note first is that this on the numerator, in the numerator, is just p tot. So p tot over m1 plus m2. That's one of the very nice things about leaving things in symbolic form. It allows you to see when you can reuse old calculations like this. And then we can just plug that straight in. 50,400 kilograms meters per second divided by 1,200 kilograms plus 1,800 kilograms, which then is equal to 16.8 meters per second. Finally, in part D, we're asked to find the total momentum using the velocity of the center of mass. And the formula for this is p tot is equal to m tot for the total mass, bcom for the velocity of the center of mass. Simply expanding out what the total mass is, it's m1 plus m2, and then vcom. Now we can already see that this is going to give us back the total momentum, because this is just, this multiplication here is just undoing this division here. So what we'll have is m1 plus m2 multiplied by p tot divided by m1 plus m2. Those m1 plus m2s are going to cancel and just leave us with p tot. So we can already see that, but it's good to demonstrate just for the purposes of calculation. And therefore I will go ahead and write in here 1,200 kilograms plus 1,800 kilograms and 16.8 meters per second. And this gives us, just as expected, 50,400 kilograms meters per second.